actually myself, so that's not much to say for, about it. But more importantly, the code related to this talk should be available on GitHub, so you're welcome to browse it as you watch the talk. And hopefully there will be enough time for us to actually browse it together. So, a long, long time ago, 3 wise men came from the east. Their names were Brouwer, Miëtek, and Kolmogorov. And well, it is a relative notion of east, but so according to the Brouwer, Miëtek, Kolmogorov interpretation of intuitionistic logic, a proof of the implication A implies B is actually a construction which takes which takes proofs of A and turns them into objects or proofs of B. So you could also say that given proofs of A, we return proofs of B, and that should sound familiar. Now, there's another closely related notion, often called propositions as types, or the Carey-Howard isomorphism, which describes the correspondence between logics and programming languages. So what does this actually say? It says that for each proposition in a particular logic, there is a corresponding type in a programming language. And so for each proof of a given proposition, there is a program of the corresponding type. So with that in mind, we can actually say that a proof of A implies B is a function which takes an argument of type A and returns a value of type B. Now, moreover, one can use the terms of a typed lambda calculus to denote natural deduction proofs. And then the simplification of these proofs corresponds to the evaluation of programs. Natural deduction was introduced incredibly by 2 people in the same year, but I'm going to focus on Gensen's presentation. And in particular, on the rules of natural deduction, which focus on implication. So perhaps you've seen rules such as these before. Perhaps you've tried to read papers which are peppered with such rules. I certainly have. As a practitioner and not an academic, I've struggled for a while before I've gained some understanding of these issues, and this is what I want to share with you. So, usually, the rule on the left is presented as implication introduction. However, for reasons which may already be obvious, and often in implementations, it is called the LAM rule. The other rule is either implication elimination or the application rule, the app rule. You can see that there is a sort of a smaller rule on top. What is going on here? So this actually introduces what's called a hypothetical judgment, which is scoped to within the area above this rule. And we shall see later how to deal with issues of scoping in practical implementations. For now, maybe we can actually try to use these rules to do something. Let's prove a theorem. Some of you may recognize this. This is a fairly famous theorem, I suppose, but for now, let's just focus on how can we try to apply these 2 rules. So, implication is implicitly parenthesized to the right. So the outermost implication here is this one. So what can we do? Well, we can assume that, well, we can call this thing A, right? And this thing B. And so we can just take it away and bind it under a new name. And I'm using a maybe unusual presentation for this proof, but this is a presentation which makes sense to me as a programmer. Perhaps, I hope it will make sense to you as well. Now we can simply repeat this by binding another variable and another one. And so you can see that we're building something up here. Yeah, we have bound three variables, each of which has a certain type. But what do we do now? Well, this is the point where mathematics becomes a creative pursuit. This is perhaps why proof search isn't an entirely solved problem. Fortunately, in our case, it's not too difficult. Well, we have the ability to get to C, right? But before we get to C, well, we have to get to B. So, and the only way we can do that is by application, right? Okay. Now, we have taken this thing, right? And we've assumed that we already got to B. So now, how did we get to B? Sorry. I should have said A. How did we get to this thing? Well, we have used application once again. Oh, this is looking a little unbalanced. All right, that's better. Now, that thing is simply the value or the variable which we have previously bound, and this thing as well, right? Now, we just repeat the same thing over here. And voila, that's a proof. Any questions? Does this make sense? I hope it does, because I'm about to shake things up a little. Too late. No, please go on. The question was, what about the horizontal lines and the text next to them, which is hardly readable now, but maybe better now. So these are just labels. They are completely arbitrary text, simply for us to be able to identify what's happening. And so they were referencing the rules on the left, but also they included, well, you can think of them as comments, but those comments have a specific meaning. Well, they were attempting to show the scope of the variables, the available scope of the variables. Now that we have turned things around, we need to fix things a little bit, because the usual order of function application is this way. And yeah, this way, right? Okay, so what's going on here? Well, when we write programs, in Haskell especially, we rarely ever write types. So there's quite a bit of types here. Why don't we get rid of some of them? Okay. How about this? We've got two applications going on now. Maybe we should write them infix. Okay. Another application, infix. Oh yeah, parentheses, sorry. So this note, this is not the default Haskell $. I'll get to that later, but you can think of it as being very similar to the Haskell $. Now, what about abstraction? Well, that's how it looks like in a programming language. We rarely write the type, so we can just omit it, perhaps. And look at that. What is that? That's a program, I think. And that's the type of that program. It may be more clear if we actually switch to real syntax. Sorry about that, but that's how Agda looks like. So Agda is a dependently typed programming language originally developed by Ulf Norell at Chalmers. It is pretty nice, especially in terms of syntax. The syntax of Agda is quite malleable. I'm not joking when I'm saying that this literally is an Agda program, and I would like to show that to you now. Oops. I thought the font was increased all over the place, but no. Okay, sorry about that. So, we were just looking at this thing here. Oops. Why is it? Oh, sorry. I thought it was already mirroring. 1 second. The simplicity comes when you have to deal with bindings. You may have heard of one of the simplest way in terms of implementation, perhaps, to deal with bindings, that is the Brun indices. However, it makes for rather unpleasant-looking object-level code. That is, one of my goals here was to be able to write theorems, or, well, proofs for them in a quite a natural fashion. And I hope you agree that this isn't too bad. But when you're dealing with the Brun indices, you have to sort of, you cannot just refer to names. You have to go back and say, okay, this will be the variable which I've bound 2 levels above, and this will be the variable which I have bound 1 level above, and so on and so on. I think dealing with actual names is preferable. There are other approaches, such as, I think, nominal bindings, which are quite interesting, but out of scope for today's talk. So this is parametric higher order abstract syntax. I believe introduced by Flipawa in 2009. What is this parametric? Well, it stands for the parameter here in this abstract data type. When we were binding variables, we were sort of putting them off to the side. That I was hoping to show that via the labels next to the rules. Now, you can think that we've been putting them into a context. Had we been using the Brun indices, we would be referring to items within that context by their index. But here, we're actually using the meta language, that is Agda in this case, to deal with the nasty stuff for us. So the context, in this case, is simply a function from types or propositions or hypotheses, and our data type of terms or proofs is parameterized by this context. Now, this isn't ideal for all scenarios. You can only really use this simple approach when you don't depend on the order of the variables within the context, because, well, with bindings done by the meta language, well, they're just there. So if you need any special conditions, you have to provide them yourself. But for now, we can just ask the context, is the variable within, well, if we're trying to say var x, for example, we're simply calling the context function with a representation of the context membership. And so we can, in this way, we can introduce a proof term standing for a particular variable. And as you can see here, abstraction is actually literally a function. It is, once again, a meta-level language function, which simply transforms context membership representations into proof terms. And given this function, we can say, okay, we have a proof term of implication. Now, with such a proof term of implication and a proof term of A, we can very easily get back a proof term of B, as it is specified in the natural deduction rules. I hope this made sense. Does anyone have any questions? Right, so this was Agda. There's not very much else in this file. Simply a definition of the language of types, a base type and implication, and that's it. And you may be interested to know that this code translates almost literally into Idris, which is a dependently typed language originally developed by Edwin Brady at the University of St. Andrews. I hope I can get them next to each other without actually decreasing the font size for once. Right, maybe this one as well. Right, okay, so that's Agda and Idris. And as you can see, the surface syntax, at least, is quite similar. Idris has some more syntactic restrictions. With Agda, you can have pretty much everything as an operator. This isn't actually Unicode. This is just a font which makes it seem like a nice arrow. But yeah, if you want Unicode, you can have Unicode. The Agda standard library goes a bit over the top, perhaps, with Unicode, which is why I don't actually use Unicode operators here, because if you don't use Emacs, they may be not very easy to type on a keyboard. Oh, perhaps I should have mentioned that these are just regular comments inserted for readability purposes. Agda requires you to be very explicit about the things which you want to use. Idris follows the Haskell way in that there's a convention. Any variable, any lowercase variable, well, sorry, any lowercase identifier is taken to be a variable. And here, Agda automatically infers the types of the variables. It is often able to do that, but not at the top level. Type declarations are required at the top level, both in Agda and Idris. So here you can see we're gaining a little bit more syntactic noise. This is because in Agda, this is a Agda lambda expression, and it automatically extends all the way down here, and this one down here. But in Idris, just like in Haskell, you either have to use parentheses for that, or do it like Perl. Now, since you may be more familiar with Haskell, I'd like to switch to that now. So it's remarkable how dependently typed Haskell actually is nowadays. You just need a couple extensions. So there's one feature which unfortunately does not have an extension, and I would very much like it to have, but we don't actually need to define the context like this. It's just done for readability purposes. Haskell is perfectly happy to accept its type in here. So what is the Haskell star kind in Idris? It's simply type, and in Agda it's set for historical reasons. The point is, there is no distinction between types, kinds, sorts in Idris. In Agda, sometimes you have to explicitly say which level or type you want to use. So this is the 0th level, and this is the 1st level. But there's not much difference apart from that. Now, in Haskell, you can't really go much further beyond kinds, as far as I know. Please correct me here. But I certainly haven't tried. And also, another syntactic restriction in Haskell is that constructors, obviously uppercase here, the equivalent constructors in Agda or Idris do not have such restrictions. And here's how our proof looks like in Haskell. To compare back to the Agda version, that's it right here. Right, so this is very much an entry-level kind of thing. I hope I haven't bored you too much. If you're interested in seeing some of my attempts at formalizing more advanced logics, there's a link in the README of the of this talks repository. I will be very happy to hear your comments, and if you have any questions, this might be a good time for them. Well, some people say that trees grow from the ground.
I have a hard time understanding. So you have this colon
$$ is actually the dollar here, and the colon is another Haskell restriction, repeated in Idris for various other reasons. So simply, if you want to write a type operator that is also a constructor of an abstract data type, it has to start with a colon in Haskell. And, well, that's just the way it is. It's another convention.
Could you also explain what it means here?
What it means? Well, it means that we are actually applying the function represented by f to the value represented by x. So this is function application.
And dropping the var.
Well, the var simply says, okay, let's take the thing which is referred to in the context by the name f, right? It's like a sort of a dereference operator, maybe, if that's not too much of a stretch. Any other questions? Yes, please. I can hardly hear you. Can you repeat it louder?
For example, you have pattern synonyms, but I didn't see any usage of them. Did you use them at all?
Pattern synonyms.
In the extension list for the Haskell example, you have it listed.
Do we have pattern synonyms?
Well, I didn't see any, so I wondered if you did. Because I love that sort of thing. So.
Oh, yes. Yeah. That's actually a leftover. Sorry about that. I was experimenting with pattern synonyms. Very good point. And they aren't actually used here.
Okay.
Yes?
How would you do proof by contradiction in this kind of system?
Very good question. So you can't actually do that in simply typed lambda calculus or in minimal implicational propositional calculus, because, well, there is no rule for bottom elimination. However, you can do this if you're working in either, well, in classical logic, right? So in intuitionistic logic, there is no excluded middle rule, but you can also eliminate bottom. So if you want to see proofs which use that, there are examples in my formal logic repository, and I'll be very happy to talk about them later.
Why did you sort of recreate the simply typed lambda calculus instead of just using Haskell syntax to do the proofs?
Well, I haven't really recreated it. I've only formalized it, and perhaps this isn't a very interesting exercise. However, the point in doing such things is to be able to explicitly work within a certain system. When you're working in Haskell, well, what system is that? It's a very powerful system. You can do things which are much more practical than this. But if you want to, to play around with a particular system, well, you have to constrain yourself somehow. And this is just one of the ways in which you could perhaps do so.
So can I try to see if I understood your talk by trying to give the message of your talk in my own words, and then you can say me whether I'm wrong or right?
Please.
So you're saying essentially that in order to build our own proof assistants, we don't really need to do anything. There are existing languages out there that basically are proof assistants for us. If we have a particular logic, like in your case, a simple propositional logic, then what we need to do is essentially give it an inductive data type description of that logic, and then we can just use the underlying programming language in order to do developments and write proofs and work with it.
I think that's a perfect summary. Thank you very much,
Okay.
Andres.
So is it in any way simpler, different to prove things in Agda or in Idris compared to Haskell? Namely, write the programs which are the proofs of the...
Well, that's a difficult question to answer, primarily because I haven't done that much proving, actually. Well, if you're doing, I think this is best answered offline. I'll be happy to take that offline. So if anyone is interested in finding out some more about these topics, these are the works that I very highly recommend. This is there's a paper by Philip Wadler, Propositions as Types, which is, I think, due to be finally published this year. And it goes into quite a lot of interesting detail about how these things have developed over the 20th century. And similarly, the report by Ant Trailstra. I've benefited quite a lot from Frank Fenning's courses, particularly a course on constructive logic and model logic. These are available on his website, and also he has given excellent talks at the Oregon Programming Language School. And if you want to learn more about practical uses of parametric higher order abstract syntax, in particularly in a final encoding as opposed to the initial encoding which you have seen here today, well, there is both the paper by Karet Kiselyov and Shan, and also Oleg's course on his own website. So that's that. And if there are no further questions, thank you very much for listening.